Okay, so we have collected this lemma. And then as I mentioned, our idea is we keep building connected graph. Okay, we first, reduce our situation into the graph with high minimum degree. And then we build this connected graph. And then we build a new one. When we are building new one, you consider this set, which have no edge extending to BI. The AI, no edge between B1 and AI. So as long as you have a vertex outside of A1, it has at least one edge extending to B1. And then you choose this B5 so that it's not entirely contained in any one of them. And it's giving new A5, which is small. And then it is connected. Then you can keep repeat it. That's the plan. And then let's proceed. So let's say consider graph G with average degree at least t, and then let's say t is ceiling of 20t square root of log t. And among all minors of G, and among all the minors, we consider the minors with average degree at least t. And we choose, say, n prime vertex n prime H graph E prime with minimum n prime plus m prime. And what we know is that this m prime is 2 times dn prime. No, 2. dn prime divided by 2. And let's say, okay, let's make it a bit bigger. So it is even number. And any two adjacent vertices, U and V, as at least, say, let's make it simpler. Let's use this as D. Let's say every degree 2D. Yeah, let's write it this way. And they have at least D over 2 common neighbors. Why? So this one is easy. You can take the minor, deleting edges as you want. So if this is bigger, then you delete edges. And this is same, and then this decrease. So you can actually make it equality. And for the second one, if you have U and V adjacent, then it has common neighborhood is like less than, and most less than E over 2. Then what happened? You contract it. Then what? You have a n prime minus 1 vertices. And the number of edges is what? D n prime minus is less than, say, t minus 1 over 2 minus 1 edge. So in the new one, we know that let's say it's G double prime, and it shows that the sorry, it's more than equal to utility this much, and then one more. So right, this is actually D here. Sorry, let's try it this way. So every degree, I was a bit confused. Every number of edges is D n prime. I mean, average is 2D. And then if this is smaller than D, then the number of deleted edges here. So every degree that leaves D. And then both n prime and n prime decrease. So this falls. Okay. So let's claim. So in here, we want to find the subgraph H1. So there exists a subgraph H1 of G prime that is T over 3 connected and minimum degree at least 2D over 3. Okay. So we claim this. How do you do it? As we have every degree 2D. So we choose a vertex B of degree and most 2D. And consider the graph in its neighborhood. So let's say H is G prime of its neighborhood. Then this H has at most 2D vertices. And its minimum degree is at least what D because of this condition. And if H is E over 3 connected, then we are done. H1, you just take the H1 to be H. Otherwise, if it's not T over 3 connected, there must be a separating set S both sides and most T over 3. And then you do disconnect the graph into several parts, and then let's say A here. Otherwise, H had a separating set F of sides and most T over 3. And let A be the smallest component of H minus S. Then what? Then this A has side and most T. Okay. Then what we do is we let H1 be the induced subgraph induced by this set A. Then what we know is every vertex has has from this condition, every vertex has at least the neighbors in the vertex set of B, the vertex of H. But we know that it's sending at least D edges. So A, this sends at least D edges. This sends also, that means because F is bounded. So this sends some edges to here and some edges to here, total D. So a vertex in A has at least D minus F, which is what? 2D over 3 neighbors in A. So this satisfies the minimum degree condition that we were hoping for. But the connectivity is what? Because of that, what? Every 2 vertex in A. So in this A, it sends certain number of edges, 2D over 3, and then this sends 2D over 3. But the entire set A has size at most, what? D. So they have at least, what? 2 times 2D over 3 minus A many, which is D over 3 common neighbors. Thus, it is D over 3 connected, as desired. So we have found the subgraph H1 which satisfies this claim. Now we are ready, and then the remaining is just how we repeatedly apply this lemma. So how? Assume we have found connected subgraph. E1 to EI minus 1 of size almost 3.1 square root of log n, say, plus 100, where there exists an edge between fpj and pj plus prime for all j and j prime and most I minus 1. And then further, let's say you have aj, so for each j, we further assume that you have aj, which is the subset of this h1 minus e1 to say bj minus 1. You delete that, and then you take all the neighborhood of this bj as well. So that's exactly, you have p1, and then you take the what? You take the a1 so that everything else sends at least one edge to p1. And then you take p2, and then you take the a2 so that everything else sends edge to b2. I mean, so we don't really care about whether vertex here sends an edge or not. So out of here, you only consider the one that's not sending an edge, and so on. And assume that each of these are actually small, d times e to the negative square root of log d over 3. And let HI be the if H1 minus B1 BI minus 1. And assume that this is connected and minimum degree of GP1 is at least E over 3. So assume this one holds. So far we have found subgraph one by one, and then so far we have make this hold. And then we want to repeat one more time to find the next one, PI, so that all the conditions still hold with this new additional one. So there are exits between PI and each one of them. And you get the AI, new AI, which is also small. And then after deleting PI, it is still connected and then have large minimum degree. And first, we can show that this HI has diameter almost 14. If not, but if there is this is connected, right? So there is a shortest path between any two vertex. 7, 8, 9, 10, 11, 13, 14, 15. If shortest path between these two at length at least 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14. Yeah, that's it. Then what you can do is you take this vertex, this vertex, this vertex, this vertex, this vertex. You have these 6 vertices. Let's say, it seems that I have forgot to say one thing, that this H1 has almost 2D vertices. So 1, 2, 3, 4, 5, 6 vertices. And you consider its neighborhood. And this neighborhood and this neighborhood, they are disjoint. And neighborhood of these vertices are all disjoint because this is the shortest path. But all of them have size at least d over 3. And in total, you have more than 2D vertices, which is contradiction. So this has diameter almost 14. Okay. And now what? We apply the lemma, the previous lemma with this parameter. How do you do it? Yeah, all the conditions are met. So your n is now more 2D. So each one of them. Okay, let's make it exactly same. So let's say your n is more 2D and n is the number of vertices in H1. And let's write it in this way. And yeah, this is n. Okay. Then you apply the lemma. We obtain a set, say, b prime I having the lemma. Then this is good in a sense that it satisfies all other property, but it's not giving us a connected subgraph that more 6 components. But because we know that it has a small diameter, this HI, so as the diameter of this HI is at most 14, and this BI prime has at most 6 components. We can add at most 13 times 5, like 65 additional vertices. To obtain a connected subset BI. And we let the AI be the vertices in H2 prime, which are not the neighbor of BI. Then if yields U sets A1 to AI, B1 to BI, and the graph HI plus 1. And we keep to that. One thing we have to check more is that these conditions are all fine, except that this condition you still have to check. But as long as I is at most t, and then t is at most what? D divided by 20 square root of d. We know that the size of the union of all dj is what? It is at most 3.1 square root of log d plus 100, and t is smaller than the d over if it's n. So n is at most 2d. Then what t is that? So 5, 6. So d over 6. This is more. And our initial graph h1 is what? D over 3 connected. And we have deleted this much. So it is hi is connected. And you have deleted this much. So its minimum degree is still. Initially it's 2d over 3, and then you delete that much, so it's at least d over 3. And finally, by the definition of BI and AI, this AI this BI delete AJ if not empty ensures that there are edges between EJ and EI or all J in previous one. So we can repeat this until we obtain a KT minor whose branch sets are B1 to BT. So this proves what we want. And maybe finally, I want to mention about Hedwiger's conjecture, which is closely related to this. So in undergraduate classes, we already learned about this Hedwiger conjecture. And we say that the Hedwiger number of H is the maximum T such that the G has a KT minor. And Hedwiger's conjecture that the for every graph, chromatic number is bounded by this head-equal number. In other words, if you have a k chromatic graph, then it must have a kt minor. Kk minor. And this one is, not too difficult for k equals 3. When say this is 3 or 4, but when k is 5, this is equivalent to 4 color theorem. And it's known for k equals 6 as well, but the proof uses 4 color theorem. And how it's related is that if you know that your graph is k chromatic, then this has a degeneracy. Okay, it means that it contains k critical graph, which subgraph with mean degree at least k minus 1. So in this subgraph, it has large average degree. So you can find the kt using the previous theorem. So the Kostrowski and Thomason's results show that give me a moment. Yeah, that shows this inequality instead of this inequality. And it was further improved by Norin, Dong, and Posel. They further improved this by if, and then the best result known is by Delcourt and Posel, showing that the bottom one can be even improved into log as chromatic number. Okay, so that's all for today. Thank you for listening. Then I will see you in the next video.